Okay, great. I hope you can hear me clearly and my screen is visible. Okay, so welcome to week 10 for the discussion session for the course on reinforcement learning. We are almost at the tail end for the course. So far, we have discussed about the value function methods, how we first started with the bandit problem, then how we can transition to the uh, full RL problem, where therein we started with the value function based method. We saw how we can make use of the advantages of Monte Carlo sampling and the bootstrapping method of value function to come up with TDE methods. Then we looked at the various control methods that are available for temporal difference method, namely SARSA and Q learning. Then we saw that for solving a larger state of problem, like for larger state space, for larger action space problem, where typically we work with huge MDPs, then value function methods aren't adequate and or computationally uh, very intensive, right? So that's why we come up with various function approximation schemes. There uh, we saw some introduction to deep reinforcement learning, namely DQN, and some heuristical introduction to actor critic methods. Okay, maybe in the last week I'll do a total coding implementation part for the DeepRL techniques that we have discussed so far. But today we'll start with an interesting concept in reinforcement learning that has been covered in week 10. So, okay. So we start with the concept known as hierarchical reinforcement learning. Okay. So for hierarchical reinforcement learning, so far we have looked at various reinforcement learning techniques, right? So reinforcement learning technique is kind of a machine learning technique, okay, in which agent learns how to perform an action by or how to perform a task specifically while by interaction with a given environment, okay. The agent here receives continuous feedback in the form of either rewards or penalties for the actions that it has taken, and then it uses that particular feedback to improve its decision making further, okay. So that's the basic crux of what RL has been so far. Now when we move to hierarchical RL, here let's say the type of problems or the type of tasks that we are targeting is much larger than the typical problems that we had been looking in reinforcement learning. So here the agent would be required to learn some complex task, and so here agent learns uh, to perform. Okay, so here the if the task that we are solving is very complex, meaning namely or meaning if we want to perform a particular task wherein the result or the goal can only be obtained by not taking a particular action but by taking a sequence of actions in a particular order, okay. So typically sequence of actions are needed. namely A1, A2. Let's say some n number of actions you need to take in order to uh, achieve the completion. Okay. Now, what happens is if a huge sequence of tasks that needs to be achieved. Let's say there are some games wherein you have to open some doors or certain locks in a certain sequence in order to reach the goal. Okay, so that's something very complicated. So the way we humans typically learn to adapt or to uh, solve such kind of problems is that we take the bigger problem and naturally we try to break it down into smaller subcomponents or subtasks of it, and then we want to achieve those subtasks while we go on optimizing on how to achieve that particular thing. Okay, and that is also true because human minds have restriction on the horizon or the future horizon to which it can see ahead. Okay, and also the memory that we have is more or less limited. We can't remember a lot of things. So to perform a bigger task, we very naturally decompose it into smaller subtasks, and then after we do that we try to learn that again and again, and over time we also learn to optimize these kind of subtasks. Okay, so okay, so this is important, and the reason is that if I have a very complex task, so there might be cases or there might be situations when the rewards that the agent get would be something very, very sparse. Okay, let me give an example. Let's say I have a particular grid world. Okay, so this is a grid world I have. Here, there is an agent. Let me denote it by color red. So red is the agent that we have. I'll also denote with some triangle notion. Okay, and the agent has to reach a certain blue colored box. Okay, so this is the goal state that the agent needs to reach. Okay, so this is typically a box. Okay, so this blue colored this thing is a box. So once you open that box, you get your final reward. Okay, but to open that box, the agent needs to have a key, right? The agent needs to have access to a particular key. So let's say initially there is some. So let's say initially hmm, there is some key lying around here. Okay, maybe I should use different notation for keys. So let's say keys are circle. Okay, I'll say okay, this circle denotes keys and this squares denote boxes, right? Now the catch is same colored key can only open same colored boxes. So let's say the agent can go here and with the that particular key, the agent can open this particular box. Okay. Now inside it, you might find some other another key which is of sorry. Inside that there might be a key which is yellow in color. Okay. So these are together. Okay. So this is one box. Okay. This also I should say is a box. Okay. So let's say you have two, three boxes lying around. Let's say four boxes. Okay. Maybe we make it slightly more complicated. From here, the agent goes here, opens another box of this particular color and finds maybe what color is left? It's a pink. Pink. Okay, he finds a pink. Okay, there's a pink colored key inside, and then here there's a pink colored box inside which let's say a dark blue. Okay, and let me close this here. Okay, so this is the problem that we have. The agent needs to finally open the blue box, only then it will reach the goal. But to open the blue box, it needs a blue key. Now that blue key lies inside some other box. For that, I need some other key, something else, right? So here we have to follow a certain sequence in order to get to the goal. So first of all, the agent should learn. So this is the agent. Okay, I'll define agent here. Okay, so that there's no confusion. The agent should learn first to go obtain a key which is lying empty, then find the corresponding box. Okay, it can't open any box. It should open the box with the same corresponding color. Okay, then find another key, open corresponding box, and do that repeatedly until and unless we reach the final goal. Okay, now if I were to do it in a traditional RL sense of way, what happens is the chances of me or the chances of an agent stumbling or coming across this action is very very rare. Okay, the reward is very sparse because the agent only gets a reward of +1 if it reaches the goal, which is the light blue box. Otherwise it agent keeps on getting a reward of 0. So there is a big sparsity when it comes to reward. Agent needs to explore much more than what it had to do in a simple problem, because here it needs to explore and find out the correct sequence, and to converge to that it might need really long time to do that. Okay, so here some level of planning or some level of abstraction is required. Okay, first of all, the agent should have a knowledge of the this grid world or this box world problem. It should have the knowledge about the placements or what key is inside what box. That knowledge should be there. Apart from that, I should be able to break it down into smaller components, and all the agent needs to know is to match corresponding key with the corresponding box. Okay, once I have broken down into smaller problems, first problem would be pick key purple. Okay, that can be done by a simple q learning algorithm. The agent can go to the purple key. Then my next step would be open box this. So that can be done. So once I have basically divided into smaller sub problems, then my life becomes simpler, right? So that's one particular advantage that reinforcement learning, sorry, hierarchical RL provides. Further, it also improves the reusability of this technique. So let's say now my goal has changed here. Okay, so let me erase this. Sorry. So let's say earlier I was going only till this particular point. Okay, let's say from here I increase it even further. Let's say I go brown. Okay, let's say I have to go till the brown point, and this is somewhere here. Let's say my goal gets increased. Okay, let's say I train it for some different kind of configuration, and now I'm testing it on some higher level or a higher version or a better improved version of that problem, which is slightly more complex than what it was trained on. So the power that hierarchical RL provides is that it can be it is able to adapt or transfer its learning to different types of environments, provided that the problem that we are trying to solve is more or less similar, right? So that's certain advantage that hierarchical RL provides. Okay, so there are typical uh, advantages of, or rather should I say properties That should be a better word. Okay. Hmm. Yeah. So the first property is we are looking at temporal abstraction, meaning so whenever we try to decompose the task into smaller subtasks, we never really talk or never really discuss about the notion of time. How much time it might take me to reach to the purple cell, or how much time it might take me to reach to the red cell, and so on. So the time notion, everything is sort of extracted. We say that uh, we say that it's done in the next time step. Okay. So whenever we are looking at a hierarchical RL framework, we always abstract out the notion of time. We say that we are only dealing with state action reward part in a general sense. Okay. Secondly, other property is the property of transfer. That is the learning that I gain, which is I didn't learn how to specifically open the blue box or how to specifically open the brown box. My learning here is how to navigate from one point to the other point. That learning is very general. I can use it to solve any sort of problem in the grid world environment, right? Let's say this is not a box world problem. Let's say this is some other problem. There is meaning finding some person, or let's say any game, any Atari type of game, wherein the uh, task or the subtask would be to go from location A to location B. So that knowledge can be transferred. Okay, so that helps in uh, the reusability aspect. So I no longer need to learn from scratch. And this is also sort of intuitive, right? Because we humans are, we don't generally forget everything that we have done so far, because most of the tasks that we human do, we tend to do it only once or twice, right? We don't repeatedly do it many number of times, any complicated task that we do, right? But we take the learnings from all the subtasks that we have done so far, and we use that particular knowledge in different other domains. Like whenever you're trying to watch a lecture for reinforcement learning, you are using some previous knowledge of basic linear algebra or mathematics in your BTech first second year, even some previous knowledge of machine learning. So we are not entirely starting from scratch about the notion of what is learning, what is reinforcement, what is a state space, what is an action space. We assume some kind of a base level knowledge, and then we start from here, right? So this is another important aspect, or another powerful aspect that a hierarchical RL framework brings in. Okay. Thirdly, we have a more powerful state abstraction, meaning whenever I am trying to solve this problem, right? I am breaking it down into smaller components. Each state that I'm dealing with, I don't really need to deal with a huge state space, right? So again, if you recollect the example that I showed in the previous slide, underline this, better highlight it. Okay, so the example that you had seen, okay, let me get back here. So the example that you had seen here, let's say I want to finally open the brown box, right? Let's say I want to open the brown box. So whenever I'm trying to solve it in a traditional fashion, I need to know the location of all the boxes that are present, all the keys that are contained inside each box, the location of that. Only then I can somehow navigate and go to that particular thing. Okay. So my state space needs to be a huge state space which contains the information of each box is present in the environment, the key that each box contains, the key which is empty and which is lying around, and the precise location where the box is present, right? Whereas whenever I'm trying to decompose it into subtasks and try to invoke any hierarchical RL framework, I only need to be concerned with the subtask that I need to do. Anything else that happens afterwards is irrelevant to me. So let's say, firstly, if I want to go from the red agent needs to go to the purple key. Okay, I need not consider any other state that might come later. So I have kind of abstracted that state into a smaller state, and that makes my learning or easier also. I need not have a broader sense of the entire state space. I have tried to abstract it out. Similarly, once I reach the purple key, I need to open the purple box. So every other box's positioning is irrelevant to me at the moment when I'm trying to solve the subtask that is given. Okay, so that way, Haskell provides a more powerful state abstraction method. Okay, it provides a more powerful state abstraction. Okay, what else? There is also another famous game. Okay, that uses hierarchical RL. So I don't know if you have seen it. There's a particular game known as Montezuma's Revenge. Okay, this is a old game. This was popular in the 90s when computer was invented, and Atari games are very famous. It's an arcade kind of a game. You might check it out. So what happens is there you have a particular man who needs to collect a key, and to collect the key, he has to go through a sequence of doors while avoiding the different obstacles, be it fire or pit or any wild animal that might come in between. Okay, he has to avoid all those things, navigate through different doors in a particular sequence in order to reach the key, and then use that key to open another door that takes him to the next level and so on. Okay, so this kind of problem makes use of uh, hierarchical RL. Similarly, if I want to do something about robotic manipulation, right? So let's say I have a robotic arm. These are examples I should mention, right? So let's say I have a robotic arm, okay, and that needs to do a pick and place operation. I need to pick an object from a particular particular uh, uh, place, location, and place it at some other location. Okay, so now there are some bunch of boxes lying around. I need to arrange those boxes in a certain sequence so that I form a particular structure, right? So I need to form, let's say, a pyramid or a big, huge boxes in a vertical line. So that way, the manipulation, the robotic arm needs to know the precise location and the placement of each boxes, and the agent will get a reward only when the final structure is built, right? So here the robots can learn different subtasks, which box to pick, which box to place where individually, and then eventually we can combine all this to perform the overall task. Okay, and it has applications in different domains, namely robotics, gaming, even in natural language processing nowadays. So just make the final statement. It provides a powerful framework for learning complex tasks. Okay, so this is like the main motive behind why we are doing hierarchical RL. So let me highlight this statement. So we know this is important. Okay, so if you want to refer back, you know that why we had discussed everything and what's the main motivation behind using hierarchical RL. Okay, now naturally, once we have defined hierarchical RL, we need to look at the different kinds of optimalities that hierarchical RL has to provide. Okay, I hope I'm using the black marker. Yes. Next, we are looking at types of optimalities. Here we go back to orange. Okay, so I'll just use the example that professor had used in his class lecture. Let's say I have a grid world again, and there's a small partition. Okay, in between there is a very small partition, and in order to go from room one to say room two, I need to pass through these two doors. Okay, I have two door openings. Maybe I should mention do it like this. It's a uh, two room map. Okay, there's a two room map. The agent always starts at okay. The agent starts at, oh, I shouldn't define the starting position. Okay, so in order to go from room one to room two, so there's two way. Okay, first is I have to exit room one, and then inside room two, based on where the goal is, I need to go for, to that particular place. Okay, so how the policy would look like? So if I want to exit room one and to room two in this case, so my policy would look like this. Okay, so I'll draw imaginary line over here. Let's say this is the imaginary line that we have. On top of that, I always move up. Here I always move down, and here I move towards the uh, door. If I am initialized here, I move here. Here I move this side. I move this side, and then I reach the goal. Okay, so this is a small partition you can think of, right? Beyond which the policy flips or changes drastically, right? Right. Delete this, delete this. Okay. Now imagine, think that we have also defined a goal location. Let's say this is a goal location, okay, that the agent needs to go. So having this in mind, how does my policy change? We need to minimize the time to reach the goal here. Okay. So let's say now my policy would be a yellow line, wherein if I want to reach the goal, I want to reach the goal in the shortest possible time. So instead of taking a longer route where here I was trying to go this way and taking this particular route, here it would be better if I just directly go this side, right, and go to the room. Okay, so this is where my policy changes. And the policy, how it looks is, I draw my separation line around here. And from here, I move up. Here I move down. Here I move towards the goal. And here I just move up and move this side. And once we are here in room two, to reach the goal, the policy is always this side. Okay. And if I'm here, I just move to this particular side. Okay. Now the question is, we want to look at the optimality. So which policy here would be optimal? So we have two different policies. One is the red policy, and the other is the so we have the red policy, and we have the yellow policy, right? So let's differentiate. Okay, what these two policies have to offer, and how we define the notion of optimality here. So what red policy does is makes no assumption of goal, only interested in solving sub problem, right? I think it's fair to say that, right? Because At every time step, the red agent is agnostic to the location of the goal or to the final global goal that the agent needs to achieve. It is only concerned with optimizing the subtask that it has in hand. Whereas the yellow policy takes final goal into account and solves sub problems with a view to minimize the global cost. Okay. So here, when I say this, the global cost, it means the final cost. I'm not interested in doing the uh, problem, like the sub problem cost, or rather, I should mention it to be the problem cost. Okay. So we have problems and we have sub problem. We have task and we have subtask. Okay. So turns out both these policies are in a way optimal, but the optimalities differ in the way we define it. Okay. So the first kind of optimality is known as, which is the red policy. Okay. So this is known as recursive optimality. And this is the red policy. Okay. So we can draw the inferencing from this particular line. Okay. So what recursive optimality does is it takes doesn't take into account the final goal that it has in mind. If it has to respect or satisfy a particular hierarchy, it tries to optimize for that particular hierarchy. So the red policy tries to optimize for each sub problem that it is presented with, and eventually whatever we get, whatever final goal we get, we combine that together and form the final solution. Okay, so this is what recursive optimality does. Second thing, the yellow policy here is called the hierarchy optimality, meaning I have to first exit the room and then reach the goal. Okay, so it has to follow the hierarchy, but so this follows from this particular uh, definition. Okay, so here it has to satisfy the hierarchy, meaning the hierarchy here is it should first exit room one and then go to room two. Okay, that keeping the hierarchy in mind, it is trying to optimal while focusing on the overall problem objective, okay, or the overall problem cost. It tries to minimize the overall problem cost. Whereas red policy is not interested in the final goal, but it is rather interested in solving a sub problem. Okay. And the third kind is known as flat optimality. Okay. So in this case, how do I define a flat optimality? So typically what flat optimality does is it doesn't even respect the hierarchy. It doesn't try to optimize on the it is simply trying to optimize on the problem cost. Okay, it tries to optimize on the problem cost without considering any hierarchy in mind. If it finds any shorter path that tends to skip in between steps, it will do that. Okay, it is trying to find the best or the global optimum solution. This is what flat optimality does. Okay, but that comes with all set of problems, and we had discussed in the previous two slides, right? Like why we don't need flat optimality. While it gives me the best possible solution, solving for it becomes very difficult. That's the whole motivation behind defining the hierarchical optimality or the hierarchical RL frameworks, right? So in this case, uh, let's say my flat optimality, uh, the policy given by flat optimality is the best policy. Okay. So how should I mention this? So the policy given by pi flat is the best possible solution that I can get. It is the globally optimizing solution, which doesn't respect any sort of hierarchy. So this solution is always better with an equal to sign with the pi hierarchy, right? Which is the solution that is trying to respect the hierarchy while trying to optimize the go to goal condition. And that in turn is greater than the recursive optimality. Okay, so let me color it in blue. Okay, each policy, or rather, I should make a comment on the policy, right? It should be the value of that particular policy, right? So I write, say, value of pi recursive, value of this. Well, basically, I'm evaluating the policy, right? So just take this into account. I hope you understand what I'm saying. I made some mistakes in the notation, but the basic idea is that there are three kinds of optimality that one needs to look at. While flat optimality finds the global solution, hierarchical tries to respect the optimality while keeping into while taking into account the hierarchy or respect the hierarchy that are present in the particular problem. And lastly, we have the recursive. It is explicitly trying to maintain the hierarchy, but trying to optimize for the subtask that is present. Okay. So here we might want to use hierarchical RL. Okay. In most cases, uh, because see, recursive policy is very idealistic, while it compromises on the solution that we have. Okay, so the solution might not be as optimal as the flat optimality, but it provides a lot of benefits, right? The way in which we can try to actually solve for subtask, and the good thing about it is that learned subpart or the learned subtask can be used in different tasks later on ahead, right? So that is one big advantage that recursive optimality provides, but then you lose out on the optimality. So there's a trade-off that is happening in these two approaches that we have. Okay, next up, I think we are done, right? Or yeah, so typically recursive is the best thing to follow. Okay, but there are some cases, right? There might be some corner cases where recursive policy might get stuck. Okay, because uh, then we might need to use a hierarchical policy. For example, a very simple example. Let's say there is a uh, laser light, okay, in between that pops up. Okay, now if I want to solve it using the red policy, exiting from the second door is a bad option for me. Okay, but it is trying to optimize the subtask, which is exit room one. But if I exit through the below door, then it's obviously bad for me. I don't want to do that. So here recursive optimality fails, or taking a recursive approach fails. So here hierarchical optimality is ideal for me. I need to do that while keeping the goal in account. Okay, so there are some few corner cases where hierarchical optimal is actually preferred over the recursive optimal in this case. Okay, so far so clear. So far so good, right? Uh, Let me see. Okay, let me just write it down. I have the definitions ready, so why not? Or no, let it be. I think I have explained it. Now it will only take a lot of time right now. Okay. Maybe we start with the next topic, which is semi-Markov decision process, okay, or popularly known as SMDP. So here, what happens in a typical Markov decision process is, in Markov decision process, what happens is you have a state ST. From here, you take, say, action AT, get reward RT plus 1, transition to state ST plus 1, okay. Then you take some action AT plus 1, get reward RT plus 2, transition to state ST plus 2, okay. And you keep doing this until you reach some state SN, okay. Getting reward of N here, let's say, or should I say S of reach S of T plus N, and here I get a reward of T plus N, okay. So this is how a simple Markov decision process works. We have a state from which we take a particular action. We choose a particular action. We go to the next state, get a particular reward, and then we keep on doing that till we reach the end state. We have a decision process that we have, and then we try to solve for the MDP that we have. Okay, this is what we have been looking at so far. And typically, how you define an MDP is, let's say you have an MDP tuple. So this is MDP tuple M. So it's typically a 5 tuple, right? The definition, mathematical definition. It consists of state space, consists of action space A, P, which is the probability transition, the probability of me going to state S prime if I am at state S taking action A, right? Then the reward for taking that particular state actions next state pair, okay? And finally, gamma, which is the discount parameter that we have, okay? Now, if you remember, we had discussed earlier, the discount parameter is actually a problem, is actually a parameter for the problem. Changing the value of lambda changes the solution. Sorry, changing the value of gamma here, the discount factor, changes the solution that we can obtain, right? Similarly, uh, semi-Markov decision process, or an SMDP, is a generalization for a Markov decision process. So here what happens is, this allows actions to have variable duration, or the actions can be executed over a period of time. So earlier, whatever we have considered in an MDP is that the actions are instantaneous. Okay. Now, in semi-Markov decision process, the actions have durations. Okay. Or what we call as durative actions also. So this, you can call it as a durative action. Okay. So you start off with some initial state T. Here you take action AT, and then let's say AT is not executed immediately. Okay. It takes some time tau to finish the particular action. Okay. So let's say this next state is reached at time T plus tau. Okay. So here the reward would also be T plus tau in this case. Okay. Next, you take some other action, which is A of uh, T plus tau. Okay. This is the action you take at time T plus tau. Then you reach some other state, which is state t plus tau prime, right? And you get a reward of r t plus tau prime. So here tau is basically a random variable which tells me the time that is taken for the agent to execute the action or for the action to be executed. Okay, and this goes on right till you reach some end state. Okay, so this is the basic difference what semi Markov decision process does in comparison to a Markov decision process. Let me color this. I see. This is the Markov decision process. This is a semi Markov decision process. Okay, so this is the important differentiation that the actions have durations. Okay, so you can here consider this time tau to be the holding time. Okay, so classically, whenever it was when it was first defined earlier, people who actually work with SMDP, they use the notion of holding time. So the way people think about it is that at time t, I've decided that I'll take action A t. At time t, I'll take action A t, but I'll do that action only after time t plus tau. Okay, that means I'm holding that particular decision, and I'll do it after time t plus tau, and that will be done instantaneously. So that's another way to look at it. Instead of saying that the action takes tau time to be completed, I say I hold my decision to take that action, and I take the action at time t plus tau, and that is instantaneous. So that way, it is known as a uh, holding time. Okay, and SMDP can actually take into account a real world constraint. Okay, so the real world constraint that SMDP takes is the gap between. Okay, so the real world constraint is that it takes into account the gap between sensor inputs or the sensory inputs Okay, so this is what semi-Markov decision process does. Now, to define the components of it for a semi-Markov decision process, for an SMDP, we again have the same components. Okay, we have the state pair, state space, we have the action space, we have the transition probability, the reward distribution, and the gamma factor, which is the discount parameter, right? So the state and the action space would remain similar to what we had seen in the MDP case, right? But the way my transition probability changes is my P here is now a joint distribution between S prime and tau. Okay, so this is the definition for the transition probability, and similarly, the reward is now the expected reward I get when I take these inputs into account. Okay, so this is the difference between MDP and SMDP. The definition of the transition probability and the reward changes here in this case. Okay, now classically, this transition probability wasn't really a joint distribution. Okay, between the next state and the transition time. Okay, so this was uh, like a separate distribution. So you compute the probability of going to the next state and compute the probability of time taken to be tau when I execute a state action pair. Okay, but with time, people have started using it as a joint distribution to simplify, specifically in the specifically in the context of hierarchical reinforcement learning. Okay, so this is the definition of the SMDP tuple, right? So next up, we want to look at SMDP learning, right? So a learning method, how to. So for SMDP learning, we look at a method known as SMDP Q learning. Okay. So this is how we actually update the states, or yeah, we update the value of the state whenever we are dealing with an SMDP. Okay. And the definition here is kind of similar, but there are still slight changes we might want to look at. Okay. So if I want to do the Q learning, we look at the update rule for Q learning. Okay, which is Q of st comma at is equal to Q of st comma at plus the alpha, which is the learning parameter, times the reward I get. So I'll just put a bar over it because we want to define what this reward at time t plus after time t plus tau steps is. Okay. Then we have the gamma parameter. The gamma parameter is characterized by the time, which is tau, because if it take tau steps, I need to discount it by the appropriate gamma parameter. Okay, and we have max over a prime q of, what do I have? S t plus tau, comma a prime minus q of st at. Okay, so here rest all the definitions are clear. Only that we need to define what is the reward function is in this particular case. Okay, so here I know the reward for an instantaneous action that I can take. So for an SMDP kind of a state, whenever we want to do the Q update, so my reward function is, so my R t plus tau with a bar is simply the discounted reward till time step tau. Okay, so you start with reward R1, take sorry, not R1. You start with reward R t plus 1, then take gamma R t plus 2 plus gamma square R t plus 3 plus dot 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 till you reach gamma tau minus 1 r of t plus tau, right? So this is the definition for the reward function. Okay, so this is how the reward looks, and how it is actually done is, if I go back to this original problem, so whenever I'm trying to execute a policy, okay, let me see if I'm still visible. Okay, I'm still visible. So if whenever I'm trying to execute the policy, so here, let's say I'm following policy, the yellow policy. So let's say I start from here, and let's say I want to move exit room one. Okay, so that's the state that I have based on the SMDP. So the reward would be taking individual steps in the grid world. Okay, until I exit the room, and the final reward would be the uh, discounted sum of all the individual rewards that has been collected in the grid world that we have encountered so far. Okay, so this is the definition for the reward function whenever we want to deal with SMDP based Q learning. Okay, what next? Next up, okay, next we want to look at options, right? Okay, let me save the progress, whatever I have, otherwise I might lose it. Okay. Okay. You can. Okay, I think my screen got stuck. Hello, can you still hear me? Okay, I think the internet got switched off here. Let me just reconnect and rejoin. Okay, seems good. Screen share is on. Yeah, uh, I think there's no echo and we can get back to options, right? Hey, okay, strange. I thought I had saved it, but okay, I'll find it and combine those two PDFs. Okay, I think saving it, put it somewhere. I don't know. I'll find it and combine the two PDFs. No worries. Just that we won't be able to go back, but that's fine. I think we can safely say that with options, we don't require the things that we have looked at so far, right? So start with options. Okay, so options is typically a hierarchical reinforcement learning framework. Okay, so it's a hierarchical RL framework. So this hierarchical RL frameworks are of three types. Okay, we'll in this course we'll discuss three types of hierarchical RL frameworks. First one is known as options. Second one is known as hierarchical machines, which is ham. And third one is known as something max q. Okay, hopefully we'll get to max q by next week. Also, this is what the course content also follows. Okay, so maybe in the next half an hour we discuss about the options and the hierarchical abstract machine framework, and then to end it up, I have a small example coded just to understand and visualize how option frame works. Okay, let's see. Okay, so we start with options, right? The first one is known as options. So options here typically refers to a macro action. Okay, Now, what's a macro action? Macro action is typically a high level action that an agent can choose to achieve a particular sub goal within a task. Okay, I can say it's a high level action, right? Meaning one needs to perform a sequence of actions in order to perform a micro action. Okay, it's like if I want to climb a set of stairs, so the macro action of go to first floor, so that's a macro action, and the micro level actions would be kind of atomic. Okay, so these micro level actions are kind of atomic, so that you have to lift your leg up, go to the first step, second leg up by this much force, this much amount, and so on. Okay, so these are all the micro level aspect, or these are the low level actions that the agents take. So typically that's how you define a macro action. And this macro action, this macro action accounts for a dynamic world map. Okay, so in case any dynamicity occurs in the real life setup, this macro action takes that into account. Okay, we abstract the sequence into a single action known as a micro action. Okay, here what options give me is sort of an encapsulated policy. So options provide a way to abstract away the details of the low level actions, and it can enable the person or the agent to think or reason about a long term goal, okay, or long term sub goals if the goal is still very high. Okay, so by using options, the agent can actually learn policies at multiple levels of abstractions. Okay, so one is a higher level abstraction wherein we are learning the macro actions, and then there could be a low level abstraction, right? So that could be the atomic small actions that one needs to execute in order to complete a macro action. Okay, so what it does is this sort of enables an efficient exploration of the state space wherein we focus on the relevant sub goals that we have. Okay, so to define an option, sorry, to define an option, it's typically defined as a tuple. Okay, so option is defined as a tuple, cool, consisting of tuple like this I, pi, and beta. Okay, so an option is defined by these three parameters. Not an yeah, by option, what we mean is a macro action. Okay, so whenever I say option, it's a macro level action. So whenever I'm defining an option, it's the action that I'm defining. So for performing a macro action, one needs to define the start state, right? Where the action would be started from. Like what constitutes a macro action? That definition needs to be clear. So first thing is the initiation state. Initiation set I, IO. O corresponds to the option O, right? Initial set of states where the option can be initiated, right? Second would be a policy. Before that, should define that, right? The yeah. So initiation state is I naught belongs to the state space. It's a subset of the state space, right? Am I still visible? Yes. It's a subset of the state space. Next up, what do we have? We have the policy, right? My policy pi of O specifies action selection at each step within the option, right? So my PIO could be a sequence of state action pair, right? Let's say I have this. So this is what my pi specifies. It specifies whatever, sorry, this should be state, right? Not step. Each state within the option. Okay. So whatever state I encountered within the option, my PIO gives me a policy to select action for that particular step. Okay. And finally, you have termination condition, which is beta O, O corresponding to O signifies option O, specifies where option should terminate, right? So this is typically a transition. Beta is a mapping from state to a 0 1 value, right? So if it's 1, it means that the macro action is executed. If it's 0, it's still in the process of execution, right? Yeah. So this is how you define the option tuple in this case. Hey, this came up surprisingly. No, no. Okay. Sorry. Yeah. Mm, now what? Yeah. So after option, okay, we define two types of options, right? One is a Markov option. So what's a Markov option? The Markov option is where a policy PIO is defined on current state. Okay. So only the knowledge of the current state is useful to define the policy pi naught. And a semi Markov option would be pi naught depends on history since the option started, right? So this is the definition for the option framework. Okay, I should write options here as well so that we know we are on the option slide. And next, we want to understand learning with options, right? What kind of uh, learning that one can do when one deals with options. Okay. Mm, okay. So we start with the basic SMDP Q learning step, right? So it will use the similar update rule that was being used earlier also. Only difference is instead of action, I make use of an option. Okay. Here this is equal to Q of S comma O plus alpha times I have the modified reward, right? R bar plus gamma times gamma tau, gamma power tau, max over next option, and then okay. So this is how the SMDP Q learning would work. But turns out there is always there is a better method to perform learning, something known as intra option Q learning. Okay. Apart from the SMDP learning, there's something known as intra option Q learning. And how intra option Q learning works is you are anyway updating the state and the option pair. Okay. That is similar to what you're doing in the Q learning. But in addition, whatever the sequence of actions that comprises of an option, we are also trying to update for that. Okay. So typically what happens is whenever I solve for the option or whenever I compute Q of S naught, what I typically get is an encapsulated policy, which is pi naught, which is what? S1, A1, S2, A2, dot till Sn, An. So basically I get a set of policies. I get a policy while I'm staying within that particular option. Okay. Now turns out I can also update for each action pair which are present inside the inside the option. Hence, we have the name intra option Q learning, right? So we can turns out we can do something like Q of S1 comma A1. Okay, so I just update the state action pair S1 A1. In state S1, I take action A1. Okay, so the update how it looks like is so we have this part plus the learning rate reward R1 plus gamma times max of A S2 comma A. Sorry, this is Q of S2 comma A. Okay, minus Q of S1 comma A1, right? So this we can solve for this quantity. Similarly, we can solve for Q of S2 comma A2 as Q of S2 comma A2 plus alpha times R2 plus gamma max over A Q of S3 comma A minus Q of S2 comma A2, and you can do it for the nth state action pair that you have. Okay. Now, question is, can you solve for this quantity? Meaning, I started from state S1. Okay, from state S1, my option started. Now, for the first next step that I reach, or the second state that I reach, can I update for the particular option that I'm still executing? Okay, so the update is with respect to the macro action, not with the sorry. The update is with respect to the macro action, which is the option, and not with respect to the micro level action. Okay, so this is separate. So can this be done? It turns out this can be done if the option that we are following is a Markov option. Okay, so if it's a Markov option, turns out we can also update it for all the corresponding states that lies within that particular option. For a semi-Markov option, this update is not possible, right? So how the update works is, so I'll just give a generalized update, right? So how the update for this works is, so let's say I have some state Si. Let me write it again. Let's say I have some state Si, comma O, which I want to update. So the way it works is I go here, take state Si, comma O, plus alpha times R1 plus gamma Q of S2 comma O minus Q of S1 comma A1. Now notice here you won't see the max term over. Sorry, this is not 2, it should be I plus 1, and this will be S of I comma O. Now if you notice, there is no max term when it comes to an option. Okay, here also I made a mistake, I think. There shouldn't be a max term. Okay, so whenever we are trying to update for a particular option, we are not trying to maximize the all available options that we have. Okay, so that's a different kind of thing. Whenever each state option pair that we take, the updation that we have is by fixing that particular option. Yes, whenever I'm trying to optimize for the state action pair, here I don't necessarily fix the policy pilot. Okay, I am trying to update it for the best possible action at each particular stage. Okay, so that's like an off policy method that we are using. So typically for intra option queue learning, the micro actions are always updated in an off policy fashion. But when it comes to uh, the option updation, the state option update and updation part, there we remove the max part. Okay, because we want to uh, not keep a history of all the updates that we have done so far. It's just a simple Bellman updation that we are doing. Okay. So this is done if let's start. If not ending at S of I plus 1. Okay. But if it ends at Si plus 1, then of course I can take the max action, right? So, or this could be Q of Si comma O. Say, what happened? Oh man. Hopefully I should get what I had written. Ah, okay. What just happened? Mhm. Is it here somewhere? No. Okay, fine. I'll just start. I'll update it later on. So just where was I? Yeah. Okay. Okay. Mm, yeah. So the final part, right? I was writing. Yeah. Let me just write it here. I'll update it in the uh, final slide. Okay. So add if I add s comma I and okay, I'll update it later, right? So we'll move to the last part. Okay, we'll quickly cover the hierarchical abstract machine. It's almost 7:30. Okay, let's see the screen. Yes. Okay, so far, okay, my screen is not visible. It seems. Yeah. Okay, okay, my screen is not visible. So did I cover most part, or did I miss something in between when the screen stopped sharing? I think the screen sharing stopped here. Let's see. Okay, we were looking at the updates for state option pair, right? So I share screen, start sharing, start off. Hmm. So we were here. Okay, we were updating options. Okay, how to close this one? Where was I? Here. Okay. This is the update part. Okay, so if it's ending at state I plus one, then I just do the simple Bellman operation. If it's not ending, okay, the moment it ends at step I plus one, I just choose the next possible action. Okay, this is the option update rule. Sorry, I couldn't write it clearer. I'll update it in the slides later. Let me see if I can do something better. At least I can bring it to the middle there. Okay, great. Okay, this is the update rule for option. Okay, next up, we look at hierarchical abstract machines. This is the second kind of frameworks that we'll look at. So here we won't go much into the details of how the learning happens. So this is just a brief overview that we are looking at. Okay, if you want to get a better understanding, it's always advisable to go read the original paper by Pars and Russells for hams. Okay, so what typically happens in a hierarchical abstract machine is the option is a simpler framework, right? But hierarchical abstract machine gives a neat, elegant framework for representing the particular hierarchy in a elegant fashion in this case. Okay, so a hierarchical abstract machine typically deals with a finite state machine. So if you are familiar with the concept of finite state machine, so there are deterministic and non-deterministic transition that happens in a finite state machine. So the first step is to build the corresponding finite state machine that kind of encaptures or encapsulates the structure of the hierarchy that is present in the system that we have. So a hierarchical abstract machine consists of four types of uh, states, okay, namely the action state, then there is the call state, there is choice state, and then there is stop state. Okay, so what happens in the action state is if the action state is invoked, then primitive action is taken. Okay, any primitive action is executed. Okay, call state basically transfers control to next machine. Choice state, whenever we are encountered with a choice state, it makes a non-deterministic transition in the machine. Okay, in the same machine, it makes a non-deterministic transition. And the stop state terminates and returns control to above machine. Okay, I've just written down the definition. Now let's understand each aspect of the hierarchical abstract machine. So you typically have a finite state machine. There is a set of hierarchy that defines what state would be called and what would be called later on. And based on that, you make certain transitions or certain choices to execute a sequence of actions or uh, a particular subtask that you have. Okay. Now let's reimagine the original box world problem that we had. We had some colored boxes, we had some colored keys, we had to open it in a sequence, right? So let's say what would be the action state here? The action state would be the primitive action, which is once I've reached the key, I pick up a key. It's a binary action. It's a primitive action. If I go to a lock, I open the lock. I move one step towards the lock. I move one step towards my goal. That's a primitive action that you can take. Okay. What's a call state? It typically transfers control to the next state. Okay. So in the core MDP that we have in a core machine, the goal is to open the blue box. Okay. Here, first, the bigger hierarchy invokes a smaller hierarchy. It makes a call that first I need to go to the purple key. Okay, so that's a call it made. So then it makes a call to a machine which is go to purple key. Then the machine goes to that particular purple key. So again, it tries to invoke some smaller level hierarchy, which is uh, initiate the task of navigation. The navigation is like take left, right, up, down, step, and so on. Okay, so we are actually going down and down the hierarchy whenever we are doing a call state. Okay, so the task is getting transferred to the lower level of actions. Okay, so that's how the hierarchy structure is built. What happens in a choice state is this typically a non-deterministic transition in the machine. So whenever we are encountering any sort of step wherein the next action is not obvious, so the agent needs to make some sort of a choice. Okay, so the choice could be a non-deterministic transition in the same machine itself, and stop state is that we stop and return control to the above machine. Okay, so it's like once you have reached the purple key, you say stop, it updates the above machine. Okay, purple purple key has been reached. Then it goes to the main MDP core MDP state, and it tells okay, now you open the purple box. So then another machine is invoked and so on. So this is the framework through which it works. Okay, so a small little example. So this was mentioned in class as well. Let's say I have a grid world again. Okay, so I have a grid world and I have some obstacles in between here. These are obstacles. Okay, so this is a room of it's a 8 shape room. Okay, so in this room, if I were to go anywhere, there are some obstacles placed along the path as well. So these obstacles are typically shaped like a stapler. So these are strewn all over. So this is how it looks. Okay, so this is a particular obstacle. If the agent is coming from here and it reaches this particular obstacle, okay, there are two ways to solve it. Okay, so once it reaches here, it follows the obstacle, goes around it, and then starts moving ahead. Okay, so that's one way. And the second way would be it actually retracts, takes few step back, and from here it chooses another action randomly. So it's like it chooses to go left and then it moves ahead. Okay, so there are two ways to avoid the obstacle here. So in this case, if I were to design a very simple hierarchical abstract machine, it's not exactly representative of the problem that we are trying to solve, but some broader representation of what a ham actually does. Okay, so let's say we are trying to just encapsulate that into a ham. Okay, so let's say we have a start. Okay, we have a start state. From there, we have a action known as follow wall. Like if there is a wall, I just follow closely to that wall. Okay, so that follow wall is there, and once I'm following a wall, I can get two things. I can either get an intersection or I can encounter an obstacle. Difference between both is, so let's say agent is started here. Okay, so it's like it goes here, 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 until it reaches here. Then it reaches accounts. It sees an intersection. Either it can go straight or it can go left. Okay, so there the agent doesn't make any decision. So my follow wall state tells me if there is a wall, I follow it. The moment I see any intersection, I stop. Okay, the moment I see any sort of intersection, I stop. And then the control is passed over to the next machine. So the task for this machine is, if it sees an intersection, you stop, and then some other machine will continue. Okay. If you encounter an obstacle, so you have a choice. Okay. Here you have a choice that you can make. And what are the two choice? One is you can along the obstacle, follow the wall and move to the other side. Okay. Or you can back off. Okay. So I introduce a new state called back off. Okay. So you retrace your step and then you take some random action, right? So this choice has a non-deterministic transition to either of these two states. Okay. Now, once I've backed off, okay, what do I do? Once I've backed off, I again can encounter two things. Okay. So I can encounter a choice state again, okay, so I can encounter a intersection again, or I can encounter obstacle again. Okay. So it's like, if I'm here, if I'm at this particular position and I choose the option of back off. So I don't back off for some random few steps, right? I back off till I encounter something. So I keep backing off till I either hit an obstacle or I again reach to an intersection. It's like I'm moving in the reverse direction. What follow wall was doing, back off is just the reverse of it. I'm moving in the reverse direction. Okay. So if I hit an intersection, I stop. If I hit an obstacle, then again I have a choice. Either I follow wall or I back off and so on. Okay. So these are the choices that one can have. So this is a very simple ham structure, ham example. Okay. Notice that this follow wall is again a macro action, right? So follow wall can call for another machine that actually does the follow wall step. Okay. So there might be steps for going up, down, left, right, or stay at the particular location. Then back off could be another machine which defines the lower level action. So this all follows a higher level action or the macro action that we are looking at. Okay, so this is a def, uh, very intuitive way for understanding how options work in this case. Okay, and the way reinforcement learning comes in is, whenever we want to make a particular choice, here uh, we are trying to learn. Okay, so the reinforcement learning, it typically tries to update the choice and the call state. So whatever updates that you're making, it changes the choice and the call state. Okay, this is how RL works in HAMS. So I think this was all that was mentioned in the class. I won't go much deeper because I am also not very familiar with the concept of ham. But if you are interested, please do read the paper that is present. Uh, I think it's 7:45. I can start with the code. Okay, let me stop this and share my screen. Meanwhile, if you have any questions, you can ask. Let me see. So is my screen visible now? Can you see whatever is visible? Okay, great. I call it remove tutorial thing. Right? So there's something. We'll do a simple code to understand SMDP queue learning and intra-option queue learning for the options framework. Okay. References, you read this survey paper on recent advances in hierarchical RL. It's a strong recommendation for any topics in HRL, which was covered in the class. And you can watch professor's lectures on NPTEL for further understanding the concept. Okay. So we start off with a bunch of imports. We are using Python. So we start off with a bunch of import. Let me also share this. Copy link. Okay. So you can edit it also. Okay. So all you need to do is you Go here, make your own copy and start editing. Okay. I'll also post this when I upload it on YouTube. Okay. Okay. Doesn't matter if there's some error coming, but I have already executed it. So I'll just go through each line. So here, the environment is extremely similar to the OpenAI Gym ones. I haven't discussed OpenAI Gym yet, but my plan is I'll do it in the 12th week. Okay. So at first glance, it might look different, but the usual commands we use are added to this cell. Okay. So we have the environment, which is the cliff walking example. So when we did the SARSA and the Q learning part, we had a cliff world example, right? So from OpenAI Gym, we imported that particular environment. I first print the number of states, which is 36 because it's a 12 cross 3 grid, right? Or is it a, yeah. So these are the number of states that I have. Then, sorry, it's the current state that I am present at, right? So it's the 36th position that I am present at, which is this. Because if I start from here, this is 0, this is 1, this is 2, 3 till 11, right? So this is from 12 till 23. This is from 23 to 31. This is 32. So I'm at, sorry, 36. Okay. So I'm at state 36 here in this case. So my current state is number 36. Total number of states that I have is 48. Actions that the agent can take is 4, which is up, down, left, right. Here the current action is taken right. I took a random action, which is it will print whatever action I took. I get the next state reward and the terminal thing. And then I find the transition probability, next state, reward, and the if it's a terminal state or not. So if I took action to go right, so I fall into a cliff, I can take that transition with probability 1. My next state is 1 because my episode ends. I again start from next state, which is 36, and I get a reward of -100 for falling into the cliff, and it's not a terminal state. Okay. So here for options, we define very simple options here. So these might not be logical options that we have, but these are deliberately chosen so that we can easily understand and visualize the Q table. Okay, so for the Clifford example, we are defining two more options. One is away, which is away from the cliff, that is to move up, and the other is close, which is closer to the cliff. I need to move down. So this is how option away looks. So opt done is false. If uh, it reaches the topmost row, then opt done is true. Similarly, closes if it reaches the bottom most, if it reaches the second or the third row, then this is set to be complete. Okay. Now how the action space will contain is, so the primitive actions are up, down, left, right. The options are away and close. So the total actions are up, right, down, left, away and close. Away and close are the macro actions. Up, down, left, right are the primitive actions. So this corresponds to 0, 1, 2, 3, 4, 5. This is the number corresponding to that, right? So 0 means up, 1 means right, 2 means down, 3 means left, 4 is away, and 5 is close. The task is, okay, let me see if I can do that. What's the issue? Monitor. Okay, let's comment this out and see what we get. Okay, here I run all these functions. Okay, I think there are some updates that have happened since I've run this. So since this is already executed, I won't do that. So here we define simple options. We have done that. So the code is we compute the Q values for the SMDP. Okay, so since this is a 12 cross 4 grid, we have 48 comma 6, 48 states and 6 actions. This updates the frequency of the data structure. Okay, and this is the exploration policy, which is the epsilon, any exploration strategy. Here we are using epsilon greedy. Task 2 is below is an incomplete code with the flow of the SMDPQ learning. You complete the cell and train the agents using SMDPQ learning. I think I have already done this. So for SMDPQ learning, you have gamma point 10, alpha is this value. So you do the updates for 1000 episodes. So you do the reset, done, choose actions according to the epsilon greedy policy, take account of the number of times each state action pair was encountered, and whatever actions that you have, if it's a primitive action, you do the normal q learning update. If it's a option, right, so you do update for that particular option in this case. Okay, so since it's a primitive action, I just do reward plus gamma times argmax of the q values of smdp. But if it's the uh, away option, so my reward bar is basically g times the reward. So I am accumulating the reward till the away action is being executed, and that gets updated in the end. Okay, and similarly for the close option, I keep accumulating the reward discounted by gamma till I obtain the final the termination condition. Okay, so using the same options and the SMDP, you implement intra-option queue learning. You might not always have to search through options, but keep this thing handy. Queue table and update frequency, you'll need it. So I did it for SMDP, wherein we are updating for each state and option pair. Now, whenever I'm doing queue values intra, so I'm also looking at the state action pair for each primitive pair. Okay, so everything else is similar. Now in the update part, if the action is a primitive action, you perform regular queue learning update for the state action pair. Now check if the action is an option. Okay, if the action is away option, then you first update for that particular option. You also update for each state action pair that comes in the macro action that you take, and then you update for each next state and the option that is also available. Okay, so this is, we are using the general idea for intra option queue learning, and same thing whenever I'm using for the close option. Now we are trying to compare the two uh, things, that is the queue table and the frequency of update for each state action pair, and then we provide comments. Okay, so this is for intra option queue learning. First one is looking at the queue values for intra option queue learning, and second is for the number of times each state action pair was encountered. Notice that whenever I'm doing intra option queue learning, my exploration is much more, okay, because I'm taking each state action pair whenever I'm doing updates for those intra level primitive actions. Okay, so here this constitutes each state that I am in and all possible actions that I can take. Okay, so from 0 to 11 is the first row. If I'm at the first row, uh, any action that I take won't have much effect. If I'm at the second row, this action 5, which is the close option, is encountered more. That is, if I'm at the second row, I should move closer to the goal. If I'm in the third row, either I move up or I move closer to the goal. If I'm at this condition, then I should definitely move up, because if I move right, I'll fall into the cliff. So that's the best possible option. And fourth row is undefined, right, for now. And similarly, for SMDPQ learning, the exploration here is also nice. And in fact, what we are doing is, in the first row, we are always looking for the option uh, close. Here also option close is favored. Here also option close is favored. And this is, I think, which is the second action. I think second action is down. Okay, so here down action is preferred. Why here down action is preferred? If I am at any state on the third row, at least on the corner, right? So if I'm at the 23rd state, which is the corner, I should go down with much higher probability. And this is, I think, captured in the Q learning and the intra-option part as well. So we can observe that in intra-Q learning, states 0 to 10 and action 5, which is the close option, has values close to -5. But in SMDPQ table, the states 0 to 10 and action 5 has high negative values. Okay, so close options has higher negative value. So this seems to justify that the close action in SMDP leads to much negative values. Okay, so these are all negative values. If I choose to do the close action in SMDPQ learning, then it will come up with a higher negative value. Okay, I think this is a simple comparison for how SMDPQ learning and SMDP intra-option Q learning varies, and you can look at the implementation of it in your free time. Yeah, I think that's all I had to cover for today. I can stop sharing the screen. Yes, I covered both SMDP Q learning and intra-option uh, Q learning. Okay, so for options framework, I whatever two methods that we have learning methods we had discussed. What was that? One was uh, SMDP Q learning, other was intra-option Q learning. Both were covered. Okay. Yeah, I think that's all I had to cover. I think yeah, that's all from my end. Let me know if you have any other questions. Otherwise, I can close this session for today. Okay, I'll wait till 8. If there are questions, I'll stay. Otherwise, I'll choose. Okay. Okay, no problem. Fine. Then thank you for joining. I hope you had a good time and see you next week. Thank you. I'll stop the recording.